Welcome to Hot Chips 28. Tutorial 1. Using next-generation memory technologies, DRAM and beyond.
So first of all, I want to get to the tutorials, but I want to mention one thing. I'm not actually supposed to be here. I'm Bryan Chin. I'm one of the co-chairs. Vidya Rajagopalan was supposed to give the presentation today. Unfortunately, she had a family emergency in India, and so we wish her the best. So she has worked really hard putting this tutorial together, and I want to recognize her efforts. She did a great job, and I will do my best to fill her shoes here today. Okay, so without any delay, I have some notes from Vidya, and I'll go through them. So why do we have a memory tutorial? Okay, everyone knows that memory performance as measured by latency, bandwidth, capacity, are key factors influencing application performance. In today's world of big data, virtual reality, machine learning, we'll hear about a lot of those things in the coming days. These parameters increase in importance, in particular memory bandwidth. As a result, the design of memory system is one of the most critical aspects of any system design. Okay, so to provide you a complete picture of the memory landscape, we've assembled a panel of speakers from both sides of the equation, both suppliers and users. So we have 3 speakers from leading DRAM vendors. We have Micron here today, Samsung, SK Hynix, who will provide a broad overview of the world of system memory, looking ahead with some focused, deep area dives into particular interest today and some other technologies for the future. We also have 2 speakers from the other side of the equation from a user perspective. As in-package integration of memory starts to proliferate, our speaker from Xilinx will address the challenges of memory integration. No discussion of memory is complete without examining it from a software application point of view, and our final speaker from AMD will talk about the role of memory in determining application performance. And finally, we'll wrap it up with a Q&A at the very end, rather than having the Q&A after each speaker. And we'll have a little panel discussion. So please hold your questions to the end, time permitting, and feel free to approach any of our speakers during the breaks or over lunch and ask your questions. So thanks for that. And with that, I'd like to introduce our first speaker, who's Thomas Pawlowski he's a fellow and chief technologist with Micron, Architecture Development Group. At Micron, Thomas has made leadership and technical contributions to many new memory systems and architectures. Recent technologies that Thomas has worked on include 3D memory, which he introduced right here, Hot Chips in 2011. He's also worked on several new memory design concepts, like the Micron Automata processor, abstraction protocols, new ECC concepts, processing in and near memory concepts, 3D cross-point system architecture, and others yet to be announced. Thomas earned a Bachelor's of Science in Electrical Engineering from the University of Waterloo. He has well over 100 US patents and serves on several advisory boards and conference programs committees. So please join me in welcoming Thomas Pawlowski.
Well, thank you everyone for showing up this early on a Sunday. Why waste your time with family when you could be here learning about all this really cool stuff, right? So, just a little bit on the title. So my original working title, this is really not very important, but what the heck, right? We're here to have some fun as well as learn something. My title was going to be Memory as We Approach the Event Horizon. But 2 years ago, Stephen Hawking very inconveniently said, you know, the event horizon doesn't actually work the way we've all described it in the physics community. And so he proposed a new name called the apparent horizon, because things can actually leave black holes. And I thought, apparent horizon. If I use event horizon, then I'm not hip. If I use apparent horizon, then that sounds like Apparent? What are you talking about? Apparent horizon, no one's going to get it. So here we go. Lame title, good presentation. Okay, let's see. Let's try to advance the slide. It's not going. Did somebody turn this on? There is an off switch, cool. Okay, so briefly, going to talk about an overview of Micron that's like a little mini Micron commercial. I promise it won't be too painful. Go into some memory technology scaling issues, a very quick view of DRAM from long ago and bringing us up to date until now. And then looking at the theme of how do we get to much higher bandwidths, which is something a lot of people really care about. And then into the topic of persistent memory and why that's important and how interesting that is. And as part of that, you've probably heard about 3D XPoint, and I'll be able to talk somewhat about that technology here. And then a quick peek into the future. Of course, this being public domain, how really cool can you discuss things that are being worked on right now? That's a challenge, but I think we'll give a pretty good view of all that. So this is part of the Micron commercial. Micron's been around a long time. It's all over the world. In fact, if there's DRAM outside of Korea, it's Micron's DRAM. And so that's been quite a wild ride for us. 2015 sales of $16 billion. A very large product portfolio. When people say, what's memory and where's memory targeted, it's probably the most untargeted thing that's built because it covers literally everything electronic that can be built. And so you can see a few of the different architecture names here, and they're covering the span of essentially every kind of product that's got enough bits to warrant having these memory devices in them. So actually, there's one number on this slide that's pretty funny. So of course, there's unprecedented growth in data that's driving a lot of new advances in systems. And you can pick any one of these areas and you can see numbers that reflect a very high growth rate. The one number that's undoubtedly wrong is the one on the IoT. Everyone's touting 50 billion connected devices in 2020. I don't think there's any possible way that that's going to happen, but it will be a big number. If it's 20 billion, that's still a lot. Okay, so there'll be all these different drivers going on. Autonomous vehicles is really fun. I saw a recent announcement that Uber said they would have self-driving vehicles on the road next year. That scares me a lot, but that's pretty cool. Okay, so promise to talk about scaling. DRAM scaling does continue, and this should be no surprise to anyone. It is getting harder and harder with every node. There's a high capital expenditure increase with every one of these nodes. What I've got on these bar graphs is actually each line represents a 2-process node leap, and each double leap gives you 100% more bits per wafer. And so the cost of doubling, you can see 3 individual metrics. So 10% more mask levels to go from 50 nanometer to 30, 35% more to go from 30 to 20. You can likewise see the non-litho steps per critical mask layer going up 40%, then up 110%. The amount of clean room space you need per wafer that you produce has been increasing slowly, and in the last 30 to 20 nanometer double node jump, 80% increase. And so you have to grow your fab size just to keep your wafer outputs constant. So when you see all these announcements about fabs being built, take that into account, right? It's not just blindly adding more capacity. It's actually part of what's necessary in order to make these bits work. Sometimes, like in the case of NAND, linear scaling just doesn't work anymore. And I love these 2 graphs here. The first graph on the top is showing how many gigabytes you get per unit area. And if we continue to grow in a planar way, you can see a pretty modest growth rate, right? But then when you go to 3D, and I emphasize that's not a Micron roadmap, right? That's a theoretical technology capability. We get back to an exponential growth curve. And each one of those points could be likened to an extra node, a new node. So just like in the world of logic, where actually the node values like 14 nanometer actually are 100% meaningless because nothing on the chip is 14 nanometer. Memory used to be true to the process node, and now with the 3D technologies, now that too will not have a meaning anymore, right? So we'll call something a 10Y process node, but nothing on there will be 15 nanometers, just like on the logic side. On the bottom, you're right. That reflects how many electrons are needed to indicate each incremental state, bit state that's in the flash cell. And you can see in 16 nanometer, we're getting down to around 20 electrons to differentiate one bit level to another. And that's in the, actually doesn't matter if it's, that specifically is three-level cell. And so we can actually measure the loss of a single electron off a floating gate. And so you know that at that point, you probably should be doing something a little different. And so again, with 3D, you can see that green line. And as we move through generations of 3D, we can choose to remain static or have a different curve coming off that point. And so with that many more electrons, you have more opportunity to do other things. For example, we can now go to quad level cell, 4 bits per cell. Whereas on the planar technologies, that's actually ridiculous. You couldn't do that. Okay, so very, very briefly, the history of DRAM has been quite fascinating. Who remembers fast page mode DRAM? There's a few old folks here, yay. Okay, so we've had quite a migration with DRAM performance really not doing very much for a long time and working its way through to extended data out, single data rate, synchronous, double data rate. I actually had the privilege of, I think, being first to invent DDR. At least in Micron, we were working on it before our external customers started asking for it. But I think it's one of those things where it was simultaneously invented in more than one place because some of our customers from a green field actually did it too. And so, but still, it was quite a good advancement, and that's kept us going for a lot of years. And you can see where it's ended up at speaking as an 8-byte wide module, 25.6 gigabytes per second. The ends in there refer to how wide is the prefetch. In other words, when you do a request, internally we get that much data, but then we funnel it into the external bits for data delivery. Low-power DRAMs have had a similar progression. I actually was the lead architect on the LPDDR2, which was the first, I think, really high performance of the low-power parts. And then the graphics DRAMs have had a similar progression, now culminating in a 14 gigabit per second GDDR5X, which who thought DRAM could ever run that fast, right? That's really pretty impressive. Okay, this might be a little bit of an eye chart when you're at the back. You can see this better in your proceedings later, but just a comparison between the different technologies, and it's interesting, but I won't dwell on that right now. Okay, so where do we go with all these requests to go to higher bandwidth? What do we do? Well, Micron did pioneer the through-silicon via-based DRAM. I had the privilege of introducing that right on this same, well, the stage at Stanford anyway. We moved locations, but we introduced that in 2011 with HMC Generation 1. Generation 2 is in production. It's an extremely tuned device. So the internal architecture, the whole point of it was, if we're going 3D, what should change internally in the DRAM? And so we actually did that. We made the DRAM units really small, And then instead of only a few, or traditionally one, or just a few, we went to 16 internal channels. And so that way, the whole point was reducing data movement, right? And so your data has to go a tiny little bit in X, a tiny little bit in Y, a tiny little bit in Z, and then you've got the data going to where you want it. And so that's something that other architectures failed to do, such as the HBM. It wasn't as thorough a rethink. That was more like an HMC copy. But then on top of that, it gave the opportunity for all kinds of new things, like putting logic right at the memory. So tiny little data movement and then doing other operations. And so with HMC, we actually have a high-performance logic layer from a foundry. We can do processing at memory. We do atomic operations. And there's quite a system performance benefit just from that, forgetting about the great bandwidth and other factors. And so really great. Now, HBM, I'm not going to talk about. Everybody else is going to talk about it. Okay, so I'll leave it to them. The organizers asked me to do a comparison slide between HMC and HBM, and I actually refused to do that because it's like, I want to be nice today, and going up against HBM is like beating up a little kid and taking their candy, so I don't want to look mean. GDDR5X is really interesting. Like I said, 14 gigabit per second, 32-bit per die. An HBM solution is a 4-die grouping as a minimum. And so for 4 of these die, we get to almost the same bandwidth as the HBM, but you get it at in the range of half the cost. And so if it's high bandwidth per dollar that people want, that's where we steer them. If it's really good system performance, then we steer them to HMC. Okay, a little bit of the details of it that I think I probably won't dwell too much on, but you can see in the graphic the basic 3D topology, the topological makeup of an HMC. And so we came up with a little new nomenclature. What you would call, let's say, a DIMM rank, a single rank, we now call a vault. And that vault, one piece of one DRAM will respond to a request. And then we've got 8 of them. And so now you can have 8 potential different layers, only one of which will respond to the request. And with each one of those, there are multiple banks. And so the number of responders to any random request is very high. And one thing that a lot of people outside of the processor architecture community, what they don't understand is that concurrency actually will increase your latency, right? Especially when you get into the tails of the distribution. And so by having a lot more responders, you actually directly impact the reduction of the latency and cutting off the tails much earlier. And so all these things, so this is a real systems-oriented architecture rather than just being, oh, well, you know, we can turn a DDR4 into a 3D stack, right? It's much more thought through than that. And then internally, there's phenomenal processing going on, and I mean bit processing as in self-test. So the part actually in the field will self-heal. It has a memory tester on chip. It will discover errors. The ECC will carry you through that error discovery, and then we investigate and say, oh, that's a hard fail, and then we kill the bit and we dial in other resources, so now you don't consume your ECC to take care of those errors. So it's wildly more sophisticated than anything that came before it. So my last HMC slide, so we have incredible reliability, really great RAS features. We do scrubbing, we correct soft errors, we have in-field repair of hard errors, we have reporting at whatever strength people want reporting. The links themselves, what a lot of people don't know is in a DRAM system, the highest error rate is the data bus. So they're all worried about cosmic and other things going on and refresh issues. Number one error by many orders of magnitude is the bus. And so we have phenomenally strong link protection on here and also a better quality of signal in the first place. So a lower bit error rate and then much higher detection on that as well. And so you can see some of the other ones. Internally, we protect everything between the layers. And then the atomic operations, I really love. On the Gen 2, we enabled that for production. And we have clever people making use of that, and they're getting 2 to 4x additional speed up on top of just getting the improved bandwidth and whatever the latency figures are. So very interesting. Then you can network the HMCs together. So if you have only a few pins, then you can chain them, you can tree them, you can have your own variety of networks without having to have 1,000 pins on your device. Okay, so let's move ahead to another interesting topic. Memory storage technology hierarchy has had big gaps in it for a long time. So we're introducing the 3D XPoint. I've got my whiz-bang slide coming up on that intro, but you can see that without some of these near memory concepts, or pardon me, the persistent memory concepts, that there are real holes in the system. And so we introduced a non-volatile DIMM that actually, you can see on the vertical axis, there's the sell price per bit. It's actually a little more expensive than DRAM because it's DRAM and a NAND all in the same package. And so with the proper software controlling it, you can actually have persistence. And so you can use it for things like databases or what have you, and still have mostly DRAM-like performance, but the benefit of not having the cumbersome reloads and other factors like that. So there's actually a lot to this slide, but I'll dwell on the persistent memory for a little bit. It is a solution available today, and so you get DRAM read and write performance most of the time, except when you have to do a bulk transfer. But you have the persistence of NAND. And so you basically have a DRAM backed up. And there's a lot of really great things you can do with that. It's enabling new markets. I won't read all of these, but databases, scale-out storage, SAP has a real great value proposition here. So there's a lot of good places where that can go. And we get really phenomenal improvements based on that. You can see, for example, in one style of database, 6 to 9x latency improvement. And so this is very significant. What does it cost you in CPUs to get a 5 or a 10x improvement, right? If you could do it, you would be paying for the extra servers, right? And so this is actually very important and vital in the system. And so, so just stepping back for a moment, I'm still kind of I was in yesteryear and today. Now let's start looking at tomorrow a little bit. So we do have future graphics and low-power DRAM architectures in work. We are expecting a DDR5. That's an in-work project at JEDEC. Optimistically, we'll have samples in 2018, production in 2019, maybe more like 2020. Who can predict, right? It's not just us. It depends on the customers and when they really want to make the jump. And you're probably aware that these architectures don't just go away. DDR3 is still in high-volume production, even though DDR4 has been out a long time. So understand what this means. DDR5 will get introduced, but it won't overnight all go to that. And I have a few details on the slide of what it's going to look like. JEDEC has the policy of not disclosing things while they're in work, and so that's about the most we're able to show without making everyone angry in the community. But you can see it's kind of the same thinking as DDR4, but doubling the bandwidth and all the things necessary to how do you double the bandwidth when the DRAM process technology actually isn't going to become twice as good, right? So, as I say, that's all interesting, but what really interests me the most is a whole new class of memory. So I'll let you feast on that timeline. This is actually really significant. We've been talking for years about emerging memories and new memory technologies, and when have you seen any of them make production, right? And so finally, now, I have issue with this slide. I'm towing the Micron line like they have in the public stuff, but honestly, 2015, Intel kind of pushed for us to talk about it at the 2015 IDF, and it really wasn't ready. We're just barely getting into production in 2016. So by the end of this year, you'll actually see things in service that use the technology. But that's actually really good, right? It's been actually in development for many, many years in one form or another. So where does it go? It's the gap filler in the system, right? So it's cheaper in cost per bit than DRAM, more expensive than NAND. It's not quite as low latency as DRAM, but wildly better than NAND. It does not have infinite endurance like DRAM does, but it's way better endurance than NAND. Okay, so that value proposition is actually really, really interesting. And so it's enabling a lot of new things to happen in the market. And I'm showing in this slide that it can go on buses such as a DDR bus, like a DRAM, or a PCIe, or other, like some kind of Ethernet, with an appropriate protocol and so on. But the bandwidth capability is actually very good. So here's a few attributes that we get from the 3D crosspoint, and I'll let you read that. But also at the same time, I'll just mention there's three issues that are quite interesting that the 3D crosspoint is addressing. So I mentioned that performance gap between DRAM and NAND. Another one I mentioned earlier in the context of HMC about effectively it's the quality of service, right? If you need enough responders and capability of each responder so that the queue depth doesn't just run away on you in these systems, and that impacts the latency, and even worse, it gives you high variability between I got lucky, and so there was nothing in queue, or I got really unlucky, and how deep does that queue go? And so with as good as NAND is, and it's a wonderful memory compared to a hard disk drive, right? Any spinning media, it's way, way faster than that. But yet there are things the NAND can't do very well because you have these quality of service issues if you're in a high performance kind of system. And so the 3D crosspoint fills that in. And there was a third point, which is actually quite important, and that is getting enough data close to the processors. If you can just fill the thing with DRAM, now just look at the refresh power of having that many bits. Right? So the 3D crosspoint energy per transaction is higher than DRAM, but the standby is vastly lower. It's really literally just a leakage standby. And so once you get to, let's say, about a terabyte of memory, now your overall energy is lower with 3D crosspoint because you're not refreshing it. So a lot of interesting scenarios there. Huh. I just lost my clicker. There we go. Okay, so if we look towards the future then, what are the implications of having this sort of memory? Well, that's really interesting. So people have been thinking in terms of all the memories independently, right? It's like, what should my DRAM system look like? What should its performance be? And what do I do with the storage system and things like that? And I actually don't like thinking that way. To me, it's all just bits. And bits have a characteristic unique to themselves. And so we just have to do the right mix. And so every system should consider how much near memory do I use. Now, I'm not defining here what the near memory is. That will be a future Hot Chips talk that I do, hopefully. Not ready to do that one this year. Then you have your, but that's very good latency, very good concurrency, very high bandwidth, very low energy per bit. Okay, then you have what I would call your working memory. That's your traditional DRAM. And that, from a processor's perspective and a multi-core CPU with network on chip and all that good stuff, you end up with around 100 nanosecond latency load to use for that kind of class of memory bit. Then we have our, what I would call the far memory. So that's where the 3D crosspoint comes in. I'm not yet permitted to say what the latency is. Under NDA, everyone can find that out, but for whatever reason, we're being kind of coy about it. However, at the Flash Memory, anyone here attend the Flash Memory Summit? 1, 2, 3, 4, 5. Wow, almost nobody. Okay, good. Anyway, one of the Micron VPs talked about an SSD product that uses 3D crosspoint, and he cited a 10 microsecond latency for that. And I'll tell you that for that product, the vast majority of the latency is not the 3D crosspoint, right? It's all the various protocols and other things that you have to go through in order to attach the SSD to those pins that will interface with it, right? And so the part is much better than that. Now, on the other side, if you were really paying attention, you saw in the very fine print nanoseconds, right? So I had a few products that use 3D crosspoint in that group, so sub 1 microsecond. But that's as fine grain as I'm able to go today. And then on the far right, we have the today the 3 bits per cell 3D NAND. And actually, what I say here is greater than 50 microseconds, best case latency. 50 microseconds would be if you get lucky on the ECC and you're using a 1 bit per cell NAND. A 3 bit per cell NAND cannot do that, right? So my slide is a little bit funny that way. It's maybe telling a slight fib. Well, I did say greater than, so I appreciate that. Greater than actually means a lot greater than in that case. Okay, but so the interesting system question is, what percentage of each type should I have? And in some cases, you don't have one of the types, right? And so then overall, you pick the blend of each bit that suits your system performance. If you're super high performance, you need a lot of near DRAM. If you're not, maybe you don't need any at all. If you're in a kind of, an okay class of performance system, maybe you don't need the far memory at all. And DRAM plus NAND is good enough, right? But we need to give everyone the option of finding some way to get done that which they need to get done, okay? So let's bring this baby on home. So what I told you is memory continues to scale, albeit with it's increasingly difficult and complex. There are new DRAM architectures in work across all the major application areas. A lot of people talk about bandwidth and 3D, and quite frankly, 3D still hasn't found its path, right? All the 3D choices are considerably expensive, and I'm shocked, having started on it in 1998, I'm very shocked that in 2016, the prices haven't come down as much as we had envisioned that long ago. But something like a GDDR5X, if you need high bandwidth for the unit dollar, that's the way to go. HMC has just a lot of tremendous system advantages for those very ultra-high bandwidth applications, including getting some processing done nearer to the memory, and also the very high system reliability. So we see the emergence of persistent memory. So our product is out right now as an NVDIMM, and that will continue, but we'll also introduce 3D crosspoint there, which I would say 2016 is the first year of 3D crosspoint production. And so the future, as I said, is blending. All kinds of different technologies, and with the overall goal of what's my average cost per bit and what's my average performance that I get out of that memory system. So that's it for me for now. We'll have questions at the panel that will come after all the speakers. So thank you for your attention, and I will yield the stage.
Terrific. Okay, great. We're right on time. This is wonderful. Our next speaker is from Samsung. His name is Jin Kim, and he's a principal engineer in the product planning and enabling group at Samsung Electronics. He joined in 1997, where he had been involved in high-speed I/O circuit design for various kinds of DRAM, such as DDR3 and 4, GDDR5, LPDDR3 and 4, and other special purpose memories. In 2003, he received his MSEE from Korea University, and in 2010, he moved to the Memory Planning and Enabling Group at Samsung, where he's worked on high-performance DRAM for graphics, server, mobile, emerging applications. He has over 50 international patents, and his current research interests are in the energy-efficient, high-bandwidth memory and processing and memory solutions. Please join me in welcoming Jin Kim.
Thank you, Chairman, for introduction. Good morning, everyone. My name is Jin Kim from Samsung Electronics. I'm much honored to be presenting in the wonderful conference. Today's topic is the future of graphic and mobile memory technology for the new applications, which is the VR and the vision recognition and so on. I'm talking about the balance of the development of memory technologies between the innovative extension and the innovative challenges. Before presentation, unfortunately, I cannot talk about the detailed, exactly the value or the feature for the future memory because of the compliance or the NDA issues. Okay, before technology in detail, I'm starting with the memory technology trend overview and application requirement. And then we will deep dive into the two challenges. The first is the high-speed graphic memory technologies, which is the 10 gigabps GDDR5 and over 14 gigabps GDDR6. And second is the low-power memory technologies applied to the LP4X and LP5. So I'm going to in addition, we are going to propose the concept of low-cost HBM and the concept of the processing in memory. And conclusion. Okay, first is the memory technology trend. Recently, we are faced with the totally different application, new waves compared to the conventional applications. They are the artificial intelligence and the virtual reality and the autonomous driving and computer vision. Some kinds of application require the disruptive innovation. In this case, require the 10 times the memory bandwidth, which is the HBM2 is the very suitable solution. And the another side is the lower power. On client case is the required more the power efficiency. In this case, the application need continuous development of memory performance and very fast response time. In terms of the memory side, it is very important to develop the memory solution for the particular applications at the right time. In the cloud system, in order to cover huge data analysis and training, we need 10 times the memory bandwidth. And however, the client system, which is the virtual reality and mixed reality, is due to the limited power budget, we need the extreme power efficiency for the virtual reality gaming and the vision recognition and the graphic performance. In such a situation, a better solution is the LP4X and LP5. In the past, the performance has been improved with the increase of core clock the frequency of a number of the core. At the same time, the memory also continuously have scaled down for the bit-growth. But unfortunately, in recently, the increasement of SoC, the performance was slow. And the memory also was faced the memory wars, which is the reliability or the processing scaling, and so on. Nevertheless, innovative application continuously required more performance. Earlier, we mentioned that we have overcome this kind of memory wars. For example, Samsung is continuously pushing, and we will support the 1x nanometer 16 gigabit mono die in 2017. There are two ways we can approach this target. The first challenge is the innovative memory for new applications, which is the VR and artificial intelligence or the vision recognition. In this case, we have to reduce the data traffic and the cost, and we have to solve some issues. So we can consider the new methodology, such as the memory offloading and the customized solution and the processing in memory. So in conclusion, we are the proposed low-cost HBM and the processing in memory. The second approach is to improve with the traditional memory solution in the conventional applications, like as a PC server or the mobile graphic. Although this kind of application do not necessarily change the ecosystem, but if we cannot figure out the value of user experience and the performance extension, it may be replaced by another innovative solutions, like as the case of a tablet or the personal computer, and so on. However, we have to balance the evolution and the revolution for the memory technology, so it's very important. Okay, this slide shows the innovative extension of memory, the performance and the power efficiency. The left picture is the performance trend in time. Now we already where is the mouse? Now we already support around 10 gigabps GDDR5 and 4 gigabps LP4X and 3 gigabps DDR4. And in 2018, we will be able to support approximately the 14 gigabps GDDR6 and the 6 gigabps LP5 and the 4 gigabps DDR5. In order to performance, we make a lot of the technical effort, and I will explain it in the later slide. And the right picture is the power. Right picture is the power efficiency to trend in time. If you guess the power of DDR3 is 100%, now we could reduce the 50% in GDDR5 and 40% in the LP4X, and the 60% DDR4 is compared to DDR3. In 2018, we are going to reduce the more around 20% of current DRAM power. I'm sure that the high-speed memory solution will be the GDDR5 and GDDR6, and the better power efficiency solution will be the LP4X and LP5. In result, the technical extension of the familiar memory is a very, very attractive solutions. Okay, actually the HBM is not an extension of the traditional memory. In the next session, the Cavium from the Hynix is going to explain in detail about the HBM. But unfortunately, the HBM is still too expensive. And we have to figure out the the low-cost solution for the HBM. So we are going to propose the concept of the low-cost HBM. Anyway, the benefit is the performance is 2.7 times, and the power efficiency is better than the GDDR5. Okay. Another innovative approach is PIM. PIM is the processing in memory. As you can see, there is a small gap between the DRAM and the CPU. In order to fill the performance gap, we can consider about the efficient solution. I think there is the processing in memory, PIM. And the picture on the right, there is two approaches, namely processing in buffer die. And another solution is processing in DRAM die. The first approach is suitable for the server or the cloud system because it is better of the parallelism. And second approach is suitable for the client segment, like as the smartphone or the virtual reality device because of lower power by using the low burst traffic. And another trend is offloading. I think the offloading is a natural trend in the industry. Its target is to reduce the workload for using for the lower frequency or the lower power. As you know, the most operation in DRAM is very simple operation, which is the data movement and the data copy. It's best simple. In this case, we can minimize the data transfer using the memory offloading and the data pre-processing or the data post-processing in DRAM. Next, I will talk about, just for a moment. Okay, next I will talk about the high-speed graphic technology. And first is the graphic application, the requirement. And I'm going to talk about the asymmetric system and the crosstalk and the equalization, the technology. And I will propose the GDDR5 of GDDR6 and the low-cost HBM and the processing in memory. As you already know, the virtual reality and the mixed reality is very hot issues in these days. In memory side, VR and the MR is new challenges. So I'd like to show the memory performance and the capacity requirement. Before the mention about the requirement, there is many variable assumption. It's like as a poly count and the frame per second and the number of the texture. Anyway, the left picture shows the maximum gaming, the memory requirement for the realistic VR. And the right picture shows the maximum memory requirement for the mixed reality. The MR is the higher quality graphics than the augmented reality. If you think about only 4K UHD memory requirement, is the 13.2 gigabyte of capacity and 1 terabyte bandwidth. And in the case of 4K 3D mixed reality, the additional 3.5 gigabyte of main memory and 151 gigabyte the bandwidth is required. Although I cannot forecast exactly, I'm pretty sure the memory capacity and the bandwidth is continuously will be increased with the diverse and the innovative applications. Okay, from this page, I'm going to talk about the high-speed graphic memory technology. In order to improve data rate, we have to focus on the respective dedicated features. This is the concept of asymmetric system. The SoC technology is good at the high speed, the logical and the functional feature. On the other hand, the DRAM is good at the capacity and the reflection function because of transistor itself the characteristic. Actually, the high-speed signaling on the DRAM is very, very difficult. So to maximize the performance, GPU have to focus on the data TX and RX training to minimize the static offset or the signal noise. However, the memory side has to focus on the noise immunity, such as the jitter or the inter-symbol interference and the crosstalk and the clock duty and the skew. From next page, I will show the memory technology for the noise immunity in DRAM. Beyond the 10 Gbps, crosstalk is one of the limitations for the high-speed signaling. Actually, DRAM use the single-ended signaling because of pin count reduction. The first, for the signaling above 10 Gbps, we have two approaches on the board level and the package level. The first technology is to improve the return path on the board level and package level. In the past, it is the common sense that the single-ended signaling is above 10 Gbps would be very, very difficult. So in order to better the return path, we use the small crosstalk package designed without the added package layer and without the cost overhead. In addition, we also implemented the crosstalk cancellation coding, which is the 3B4 coding for the worst data pattern. In the past, we couldn't use this kind of the coding in DRAM. In this case, even though the cost overhead was minimized and the complexity of circuitry slightly increased, moving forward, if we require higher speed signaling, we can consider the 8-bit and the 9-bit coding. Okay, another limitation of signaling over 10 Gbps is the inter-symbol interference. So generally, in order to remove the ISI, we can consider two kinds of equalization, the CTLE and the DFE. As I said, DRAM is single-ended signaling, is very, very sensitive to the high frequency signaling noise. So we think the DFE is more suitable solution to remove the ISI in over 10 Gbps signaling. With the DFE scheme, the exact GPU training method is most important. The technical key point is feedback speed in DRAM. Because of transistor natures, using the high-speed clock technology, the DRAM can give the left feedback to the GPU or the SoC. That is the key point. Okay, let's talk about the maximum speed target of traditional DRAM, only with the single-ended signaling. The maximum target of GDDR6 is the 16 Gbps on 1.35 voltage system. Fortunately, we still have several technologies that we can use in DRAM. The first, in order to reduce the jitter, we can use the WCK per byte. And as I mentioned previous slide, in order to reduce the ISI, we can adopt the per-bit RX and the TX equalizing using the DFE. And another idea is to minimize crosstalk on board level and the package level. The picture on the right is target timing of GDDR6. The GPU or SoC do not need to change the clock and address the frequency. Only WCK and the DQ frequency is doubled. Furthermore, to maintain the same core cycle, we changed the burst length 16, and for data granularity, we changed the 2-channel by 32. However, the data rate of DDR6 can support 16 Gbps using the same clock and the same address frequency. Although I already mentioned briefly, HBM2 can support the innovative high bandwidth performance, but we have to balance between the performance and the cost associated with the 2.5D or the stacking structure and so on. So we have defined the low-cost HBM for consumer or the client the segment. In order to availability and the cost benefit in client system, we can think of some kind of the challenges. The picture on the left is the conventional HBM the structure. In order to cost down, we can remove the buffer die, like as the master slave the structure in the TSV the DDR the device. And the HBM had around 1,000 the pins, but we can think about the reduction of the number of the TSV, and organic is better the cost-effective solution than the silicon interposer. Moreover, we can support a similar bandwidth in the higher speed signaling. In result, include this kind of approach, we have to challenge the best solution. So I think that is the true innovative memory solution. As I mentioned the previous page, we can accelerate deep learning processing using the HBM buffer. In these days, the GPU and the graphic memory performs the deep learning for the parallel processing. Strictly speaking, the GPU is not a dedicated solution for deep learning because there is the extra overhead for the real graphic features. Recently, the dedicated accelerator appeared the higher bandwidth memory. And if data processing is very simple convolution and subsampling, and we will have to consider how to minimize the data movement. For example, we have already the HBM buffer. We will be able to include the simple metric function or the communications between the HBMs. So we may be able to support the best solution for the artificial intelligence industry in the cloud or the server system. Okay, next I will talk about the low power. Let's move to the other application situations. It's low power memory industry. Recently we are faced with the high performance, the demand of a mobile device. Now the consumer device require the PC level, the graphics at the mobile, the power budget. So I guess you guys already have seen this kind of the pictures or the graphs. Anyway, the picture on the left shows the performance of each application versus the thermal design power. On the right side is the power dissipation trend in time. Although the dynamic and the static power is sharply increased, but thermal limit increase is very small, very slow. Actually, the power improvement, only the SoC and the DRAM itself cannot enough. So in result, SoC and the DRAM itself cannot solve this kind of the issues. We have to collaborate with exactly closely to find out the best solution for low power. Okay, let's dive into the low power memory technology. We are still continuously working on what we can for low power. The picture on the left, the LP4X have the same VOH margin with the LP4, only using the 0.6 voltage, I/O voltage. The picture on the right, although the low core power is not reduced, but we could manage to reduce the 45% I/O power. Even this kind of the small changes, we can provide the power saving of around 20%. Nevertheless, LP4X have the high-speed signaling of 4266 megabps. Okay, this slide shows the target of LP5 and several ideas for low power. The speed target of LP5 is double compared to the LP4, and voltage will be potentially lower than the 0.6 voltage. the future power level is reduced around 20% compared to the LP4X. In the future, the power, the efficiency is continuously reduced in time. The left picture shows the operating power reduction, but the reduction of standby power is not easy. So we have proposed several ideas for low power. The first is the command-based data clock, and the frequency scaling for the first is the command-based data clock and the frequency scaling for the standby power. So with this technology, we expect to be able to reduce the power by over 50%. And second is the center top termination of WCK for differential signaling is power. We estimated the operating power can be reduced in excess over 5%. And finally, in order to reduce the reflection current, we propose the deep sleep mode. Using this mode, we can achieve IDD6, the reduction of 30%. Included this kind of technology, we have focused on the various items to reduce the power. And this is the different approach to have lower power consumption. Recently, all-in-one VR or the PC-like the smartphone required simultaneously PC-level graphic and the mobile power budget. In this case, each chip and the functions need to use common DRAM through the common memory bus. In order to cover this operation, the extreme memory bandwidth is required. But unfortunately, with the limited power budget, we cannot use even full bandwidth. So in order to reduce the unnecessary data movement and the frame rate, we can use the memory uploading from accelerator or the SoC to memory. For example, pre-processing and post-processing with the drone or the virtual reality device. Regarding pre-processing, there are image and the gesture recognition using the deep learning algorithm. Regarding the post-processing in VR, we can consider time warp and the range distortion and the chromatic aberration, the correction, and the frame rate control. However, this approach requires close collaboration between the SoC and DRAM. And we'd like to propose the proof of concept project with the processing in memory. Okay, the conclusion. As I mentioned the previous slide, future application required extreme performance and ultra low power and very cost-effective solutions. And in order to overcome this kind of barriers, we have to make an effort to extend the traditional memory value, and we have to balance the development between the innovation solution and extension solutions. However, the SoC and the DRAM itself cannot solve this kind of issues. For example, the low power and the extreme the bandwidth. So we have to collaborate with each closely to find out the best solution for industry. Thank you for your attention.
Great. Okay, we had some great presentations this morning. As I mentioned, we're going to have a Q&A session at the end of the tutorial, which will be right before lunchtime. Okay, so we have 3 more talks, and then we'll have our little Q&A and then lunch. So our next speaker is Kevin Tran. Kevin is a Senior Technical Marketing Manager at SK Hynix, where his primary focus is on advanced memory solutions for high-performance applications, including networking, high-performance compute, and automotive. He's also the HBM Program Manager for SK Hynix America, has been developing the ecosystem to enable HBM in 2.5D integration since 2011. Kevin has over 14 years of experience in applications engineering, technical marketing in the semiconductor industry. Previously worked for Atmel, Micron, Nanya, and prior to joining SK Hynix. So please welcome Kevin Tran.
Thanks. Well, hello and good morning. Welcome back, everyone. It's a pleasure to be here and to talk to you about the high bandwidth memory device, or HBM device. Years ago, customers approach us and ask us to deliver or to provide a memory solutions that offer higher bandwidth at optimized power. And we looked at the HMC at that time as well as HBM. And as a company, we decided to continue with the innovation of high bandwidth memory. And since then, it's been a few years from then, but customers have adopted the HBM in almost all major applications. And I will talk about that in my presentation. Tom from Micron talked about, he didn't want to talk about HMC. I'm going to pick on Tom a little bit, but HMC versus HBM, in his case, he said that it's kind of like big kids beating little kids and taking their candies. But I feel that with HBM, the little kids beat up the big kids, took their candies, and made them grounded as well. So time out for the big kids. But anyways, getting back to the serious topic on HBM technology. You know, we've seen the rise of social media and the mobile data growth or explosion of mobile data with that. And to me, that's really the first phase of data growth explosion that everyone in the industry is talking about now. The next phase, I think, would come with the deployment of 5G network. And with that, there's a host of other technologies that will leverage 5G network capabilities. We're seeing applications like augmented reality, virtual reality, as well as autonomous driving and IoT devices, for example. All of these applications will no doubt increase or will generate massive amount of data. But what's further than that is that not all data are created equal. And so what we're seeing is that the level of complexity within the data set themselves it varies between applications and also within the applications themselves as well. And that means the commercial value for this data becomes quite varied in nature. And so being able or having the capability to process this massive amount of data and selectively analyze the valuable data can bring in tremendous sources of new revenue for the industry. But how do we get there from where we are today? For the longest time in history, we continue to hear that system performance would have to improve. And in the networking side, from the access point into the core of the network, as well as into the data center, for example, all of these systems would have to increase their performance. And oftentimes, it's the memory subsystem that creates the major bottleneck to realize the next level in system performance. So the industry and ourselves have been looking at high bandwidth memory architecture to deliver or to address these memory bottlenecks. And in my talk today, I'll give you an overview of the HBM device, its architecture, how it delivers the bandwidth that it does. And then we'll talk about some of the key features which my customers are always interested in, quality, reliability, and the testability of the device. So with that, just myself. Jin from Samsung talked about the major trends in the semiconductor industry as well as in memory technology. Systems continue to innovate. We see high performance computing adopting and continue to improve on the number of processing cores, and that would require a massively parallel memory subsystem to deliver the bandwidth that they require. In networking as well as in graphics, DRAM memories are used as a packet buffer or a frame buffer memory. And the rate at packet buffering increases in networking, and it sometimes is dictated by the Gigabit Ethernet standard. Graphics, the fill rate continues to increase with 4K TV or high-definition TV, for example. And so from a DRAM vendor perspective, we feel that memories that are based on TSV technologies, the through-silicon via technologies, can deliver the next level of system performance. Essentially, what TSV is it's an interconnect technology that allows die to be stacked vertically. In our case, the DRAM die, we can stack them vertically, and we can bring out the signals to the package or to the external world without having to use wire bonding technology. And this is an innovation because when you forgo the wire bonding technology, you're able to reduce the package size. And so that's how we deliver smaller footprint on the HBM device without using wire bonding. Another benefit of TSV is that when the package is smaller, your I/O signals from the die themselves out to the package level is shorter. And so you're able to save or reduce the capacitance on the I/O. Therefore, you're able to drive faster signals. And also the I/O on the controller side, the circuitry can be smaller as well. So that saves power. TSV also allows the HBM device to pack much denser signals on a per unit area. So with that, the HBM device is able to pull out 1,024 I/Os per single device. And so TSV was the technology that allowed us to develop memories like the high bandwidth memory. So for now, I'll talk about the system architecture or the architecture of the high bandwidth memory itself. What exactly is HBM? The figure here, and the pointer doesn't work, but in a commodity DRAM, a discrete DRAM solution, the die, I/O on the die is routed out to the package via wire bonding, and then at the package substrate, it's connected to BGA ball. I think we all know that. With the HBM device, with the figure on the top right there, we have TSV that runs down the center of the die. And then at the bottom of the die, we call it the base die. The signals are then routed from the TSV regions out to the PHY area. And to integrate the HBM into a system in package or into the same package with the processor or an ASIC, the processor would then interface to the HBM through an interposer. HBM itself is really agnostic to the interposer technology, but there are reasons why we see in the industry that all commercialized programs with HBM in 2.5D integration, they're all using silicon interposer. We do see alternative solutions such as organic interposer and organic substrates with embedded organic interposer becoming commercially viable within the next 1 to 2 years. So that's exciting for the overall HBM ecosystem. The figure on the bottom right here shows the layout, the functional area of the HBM device. The dark blue area is the direct access ball area, which customers will route the signal out to their end package, BGA ball. And that allows DRAM vendors as well as customers to run specific testing to ensure that the device operates correctly or to verify the functionality. DRAM vendors also use that to do their failure analysis. So in terms of the mechanical aspect of the HBM device, JEDEC, the standardizing body, has agreed that the Z height will be 720 micron. The XY dimension will vary between DRAM vendors, and this adds a level of complexity in terms of the supply chain for customers adopting the device, because depending on the 2.5D process and also the integration process and the interposer design, customers may have to use different interposer designs for each DRAM vendor. So there is a desire within the industry to have a universal interposer that will support all DRAM vendors' HBM devices. So the talk is to continue with the foundry partners as well as with the DRAM vendors themselves. The central figure shows the micro bumps on the base die of the device. JEDEC defined them to be in a staggered formation, and the base dies, the micro bumps are, for us in SK Hynix case, is 26 micron in diameter. The pitch is 55 micron, and so it limits, in terms of the type of interposer technologies that can route, or the packaging technology that can route and interface to these micro bumps. The figure on the right hand side bottom figure shows the top view of the HBM device. The top die of the HBM device is exposed, and it helps with the heat dissipation from the bottom of the die. There's side molding that we add to the lateral aspect of the device, which helps in the overall improving the integrity of HBM. From a functional perspective, I mentioned that HBM device has 1,024 I/O. JEDEC defined that from a base die view, the HBM will have 8 channels. Each channel will have 128 I/Os. So total, you get 1024 I/Os. DRAM vendors that are introducing HBM technology can support the device up to 2 gigabit per second. So the total aggregate bandwidth for all these channels can range from anywhere up to 256 gigabyte per second of bandwidth per device. I/O-wise, it's still at 1.2, so compatible to the DDR4. What I show here is a depiction of an HBM architecture. Again, as I mentioned, JEDEC defines that the HBM itself has 8 channels. It doesn't define how DRAM vendors should architect their channel architecture within the die themselves. What I show here is an HBM device with 4 stack of DRAM, and each stack has basically 2 main channels. Some design can have up to 4 channels per die. But in this case, I show a 2-channel implementation on each die. There is also a pseudo-channel mode that essentially breaks down the structure of each channel into half. So each pseudo-channel has 64 independent I/O, and they share the same command and address lines. What it does is that it allows the data granularity that you send across the I/O bus to be smaller, and it improves the overall power efficiency of bus utilization. When we compare HBM to existing commodity DRAM, we see that in terms of bandwidth, HBM can theoretically provide much higher bandwidth than a DDR5 solution or your existing DDR3 or DDR4 solution. Power-wise, the HBM, when we compare it on a bandwidth to power to pin basis, so what I call the effective power efficiency, it exhibits very promising power reduction. We see that HBM, the current generation of HBM, can save almost 70% of power when compared to a DDR3 or DDR4 implementation. A lot of the processors today and going forward, it's not uncommon that they require bandwidth from the memory subsystem to exceed even 1 terabytes per second. And today, to implement that solution, you would need to use 40 pieces of DDR4 modules running at 3.2 gigabit per second. I haven't seen that solution at that speed in the market today. A more eloquent design would be to use an HBM solution with 4 pieces delivering 256 gigabyte per piece. And all of this can be packaged into the same packet as an ASIC or a processor, and it takes up about 50 by 50 millimeter square. And so for these benefits, we're seeing HBM technology being adopted across the industry. In high-performance computing as well as server, we see that HBM essentially acts as an L4 level cache, albeit very high bandwidth and much higher density than an embedded type of cache can provide. And in cases where the processor requires higher density, it can always go out and get that from an external DRAM source like a DDR4 module. HBM is extensively adopted in networking as well as graphics. And in this case, it acts as a buffer memory that offers, again, very high bandwidth and very cheap power as well. We're seeing designs in desktop and mobile, not mobile, but notebook, that are evaluating and adopting the HBM technology, again, for the same merits that I have discussed. Currently, HBM is available in 3 product lineup in the industry, ranging from 2 gigabyte up to 8 gigabyte densities. The beauty is that all of these density solutions have the same footprint, and they also can reach the same or provide the same bandwidth. So in systems where a vendor would need a certain level of flexibility in their SKU, for example, they can adopt a 2 high version, a 2 gigabyte version, or in a higher performance SKU, they can use a higher density 8 gigabyte solution. So this is very attractive for customers adopting the HBM technology. So now let's switch over and talk about some of the features that allow customers to sleep at night, basically. This is a new device that haven't been done in the memory industry. Sits in the same package as an ASIC, and oftentimes the ASIC can cost a lot of money. So people lose sleep at night thinking, oh my gosh, what happened if I lose a bit on the HBM? So there are ways that DRAM vendors built in the device as well as in their test flow to ensure high quality, as well as providing the flexibility to test by our customers after the device have been packaged. Since HBM is not a discrete memory device, DRAM vendors came up with a different test flow. For discrete device, after the wafer has been tested at wafer level, singulated and packaged into discrete device, it's very easy to test them using your ATE testers, for example. With HBM, in order to emulate the stress test at the package level, DRAM vendors have developed a KGSD test flow, or known good stack die test flow. And using a built-in self-stress test, it emulates the stress that the device would experience, if you will, had it been an external or discrete DRAM component. So when we start at the wafer level, the core die of HBM goes through the same test flow as an external discrete DRAM at the wafer level. The base die will be tested for logical functions using an IEEE interface. After DRAM vendors stack the core die on top of the base die, it goes through the KGSD test flow that I mentioned. So DRAM vendors are able to test as well as correct for any failure or any failed cells. And then they can do speed testing as well for speed binning. Beside from this, the HBM have certain built-in features that allow customers to test the device after it's packaged into, or after it goes through the integration process. Of course, at the system level, the device support ECC, so you're covered in that sense. The PM-BIS or programmable BIS test that DRAM vendors provide allows customer to test the device, detect failure, and correct the failure, whether at the DRAM cell level or at the micro bump level. I talked about stressing the device using the BIS engine. That helps with for customers to run in their manufacturing line as well. In terms of guaranteeing or ensuring that the package meets our quality standard, we also, DRAM vendors also develop a proxy package, which essentially is an HBM on top of an active interposer. And then they would bring out the signals using a GDDR5 package. And all the signals are muxed so that the DRAM vendors can test all the cell regions within the HBM device. And that's how they basically correlate the functionality of the device and monitor the quality level in production. I talked about being able to test the HBM device. The figure on the left-hand side here shows that you're able to test the device using an IEEE 1500 interface. There are test flows that are defined at JEDEC to do this. And also from a DRAM cell perspective, as well as microbump or TSV, customers can use post-package repair capability. There is a hard repair function as well as soft repair that customers can do when they detect a failure at the DRAM cell or at the microbump area. I won't go into the repair mechanisms. Another critical topic in the HBM and 2.5D integration is thermal management. Oftentimes, the HBM device sits very close to an ASIC or a processor that runs at 150 watts, sometimes 200 watts. And so being able to dissipate the heat from the base die up to the top core die is essential. And we have seen, the studies have shown us that adding thermal dummy bumps between the base die and the core die up to the top die will help to draw the heat, if you will, from the base die to the top die, and then subsequently allows that heat to be dissipated by heat sinks, the package heat sink. And it follows a curve of diminishing return. The more thermal dummy bumps you add, the better the heat dissipation, but it tapers off at a certain level. And so the HBM device that you see in the industry will have thermal dummy bumps built into them throughout the device to allow heat to dissipate and maintain a thermal delta between the base die to the top die at a specified area, region. This is just a list of collaterals that we see available from DRAM vendors to help with designing for functionality, for example, as well as the mechanical and interposer design. Thermal simulation is important, and so we see thermal models available to all customers from the DRAM vendor. Now I want to talk about a little bit about the what we see for next generation of HBM technologies or HBM variant. In order to expand the adoption of HBM technology, DRAM vendors would have to address all of the key parameters that I listed up here: cost, form factor, power. In some cases where cost is a limitation to adopting the technology, having ECC or without ECC may help in that sense. Also improving in bandwidth. Currently, all of our customers are asking for 2 times the bandwidth of the current generation. So we are targeting 512 gigabyte per second per device in the next go-round. I want to talk about cost. HBM itself, the integration of HBM adds extra cost for the total TCO. And so we see competing technologies from a supply chain level. For example, the organic interposer, when it comes on board, it will help with the cost in the overall ecosystem. And also, as we move towards the 2020 timeframe, HBM production will reach an economy of scale, and so overall costs will be relatively attractive for mass adoption of the technology. And so, as I mentioned, HBM, it's a JEDEC standard. It delivers high bandwidth at very optimized power. And there are measures that DRAM vendors built in to ensure that it reaches, it provides quality, reliability. And also there are measures to testing the device and ensuring quality level after customers have packaged them. So with that, thank you.
Thank you, Kevin. So now we've heard from 3 DRAM manufacturers, and it's meant to be a tutorial. It's not a conference where we're going to debate each other about the merits of different technologies. It's clear there's a lot of different technologies that can be leveraged, and now we're going to change the program a bit, and we're going to talk with some people who use some of this technology and find out what their experiences are. Maybe that'll help you guys in some of your future designs. So our next speaker is Suresh Ramalingam from Xilinx. Suresh holds a PhD in chemical engineering from MIT. He has 20 US patents, 2013 SEMI Award, Ross Freeman Award for Technical Innovation, and numerous Best Paper Awards from many different conferences. He started his career at Intel, developing organic flip chip technology, first implemented on the Pentium 1 in 1997. He co-founded Cyan Photonics, which was acquired by JDS Uniphase, where he helped develop DWDM modules used by major communication companies. As a Xilinx fellow, he currently manages advanced packaging interconnect technology development, including TSV/3D for Xilinx FPGA projects. Please welcome Suresh.
Thank you. Thank you. Thank you, Bryan, for the introduction. So this is my first attempt to present at Hot Chips conference. I'm usually more of a technology and supply chain guy, but the worlds are colliding so much, and the interdependency between design, technology, supply chain, and system. So in my presentation, I will attempt to give you a flavor for all of these aspects from a user perspective. So for FPGAs, I guess you have a different laser pointer here. Okay. So for FPGAs, one of the strong motivations for HBM usage is data center applications. So I will start off with how FPGAs play in this area as a motivating factor. And some of our earlier speakers, I think Kevin touched upon it. So there is a plethora of packaging options that are coming out depending upon whether the solution is coming from a foundry or a substrate provider or a assembly provider. So I'll try to give a landscape flavor in these options. And then from an interposer design perspective, what are some of the things to be taken care of as a design house or a product solution provider. And supply chain, this is more specific from a silicon interposer standpoint. I will give you an idea of who are the players that we work with and other fabless companies work with. There are certainly some challenges that come about when you're trying to satisfy system use cases with these combined SoC plus HBM solutions. There are business challenges. If you can think of telecom applications, the the system product lifetime could be 10 years, for example, right? And there are some challenges there. But here I'll focus more on some of the thermal aspects for today's talk. I'll conclude with a summary here. So in data center, FPGAs are mainly used as accelerators, and typically in conjunction with a processor. And they sit on PCIe bus or some kind of a cache-coherent interface to offload tasks or workloads, so the CPUs could be used for some other functionality. And typically, if you look at data centers, right, the workloads themselves could vary quite a bit during the day. For example, maybe in the morning, the activity could be oriented more around people checking news. Maybe by as you progress through the day, it could be more financial heavy transactions such as stock trading, buying and selling. As late afternoon approaches, when kids come back home from school, it may be more social networking heavy. Maybe at night it could be more video streaming, such as through Netflix. So the FPGAs, a single FPGA could handle all these different kinds of workloads because of the reprogrammability. And so the programming itself is done in the what is called the soft GUI. So the hard shell is typically the peripheral interfaces, which are not programmed like the DDR or PCIe, and it's programmed internally in the soft GUI area. So acceleration itself requires a lot of memory bandwidth, and this is where the HBM comes in. And FPGAs also being naturally quite parallel in how they operate. In conjunction with the high bandwidth memory, you can have parallel computational workloads. So getting into the technology, so here I'm focused more on side-by-side integration of SoC with the HBM. Could be a single HBM or multiple HBM, depending on the design needs. So in the y-axis here, it's really a metric for comparing technologies on how many die-to-die interconnection wires you could get. For example, if you take a silicon interposer approach, and you have a SoC and let's say a 20 millimeter wide SoC, the silicon interposer itself could provide you metal pitches that are 1 micron or even finer. So you could have more than 10,000 wires across for the interconnection. Whereas if you take a regular flip chip substrate, for example, the finest metal pitch could be 20 micron. You get far fewer wires, right? So there are a whole range of technologies that are trying to fill this region, right? And if you take HBM, such as a 4-high stack, you could need up to 2,000 wires for interconnecting the phi in the SoC to the phi region in the HBM. And that may push towards 4 micron metal pitch or finer with multiple layers. So let's start looking at the options here. So Cisco published a paper at the ECTC, which is the premier packaging conference this year, and they touched upon an organic interposer option. So in this case, there are vendors such as Kyocera or Semco, which is a Samsung substrate house, which have some offerings in this area. And in the organic interposer, the ASIC or FPGA is assembled on an interposer through C4 or finer pitch interconnections. In that case, it would be called microbumps. And the interposer itself is assembled through C4 to a regular flip chip substrate. So the difference is the organic interposer offers finer density than the regular substrate. And in this case, 10-micron pitch is the minimum rule. So you end up needing probably about 8 layers or so to hook up the SoC to the HBM if you want to use the full features of the HBM. So what is the pros and cons? The pro is clearly this is a little bit more, from a supply chain perspective, what people are used to. There's a substrate provider and an assembly provider. It makes it a little simpler. The con is, you have to still worry about things like latency, for example, with this approach. There are even more advanced options that are coming out, still organic-based, which are trying to push the pitches down to 4 micron or under. And this is where there are a lot of competing options. So Intel came out with their EMIB, which is really silicon bridge embedded within the organic substrate. So if you look at this here, they attempt to solve the fine pitch problem by using a silicon interposer. The silicon interposer itself is thinned quite a bit and embedded within the organic substrate, and it's connected through micro bumps, and this could be a HBM on the other side here. The interesting thing about this option is it's supposed to reduce the cost compared to a silicon interposer because the interposer is used only at the interface region, so therefore reducing the area. But there are still some more challenges around how you maintain the coplanarity of the substrate and the bumping itself during the assembly process, right? So those are all trade-offs to be worked out. And if you go back to the other options, so the fan-out is something that comes from either the foundry or the assembly provider. It's more a wafer-level integration method. And you have the fine-line options, which are more coming from the substrate provider, right? So I'll touch upon those next. So if you look at the substrate options here, what the vendors are looking at is, unlike an organic interposer, they are trying to integrate the fine-line layers here directly on top of a regular substrate. So so this reduces the number of assembly levels and also probably keeps it more simpler from a supply chain standpoint. So the idea here is you would take, usually these are end up being more photoimageable kind of materials, so you can pattern to finer resolutions such as 2 micron. And the vias also that interconnect the layers scale down. So if you look at a normal flip chip substrate, the vias could be 50 or 60 micron sitting on a 90 micron pad size. So that definitely reduces your vertical density for routing. So in these fine layers, these vias get down to 10 micron on a 20 to 25 micron pad size. So these are some of the escape schemes going through a 55 micron bump pitch. And there are different substrate players here that I've listed here that support these options. And so if you look at it from a foundry or like a TSMC perspective or assembly vendors like ASE, Spill, or Amkor, there are, again, a couple of options. So TSMC, as you know, promoted their info technology, which is really currently satisfying more the mobile space. But if you can extend that technology, so what you do here is you take known good dies, and these are reconstituted on another wafer format through molding process. And then this wafer goes through subsequent steps to create these RDL layers that are built up on top. So this is what you would call a RDL last approach, because essentially you are taking known good dies and then doing quite some intensive post-processing with it. So if some folks are concerned about the yield loss on these fine line RDL layers, the other approach is these layers are patterned on a temporary carrier, and you use microbumps instead of vias to interconnect them to the RDL layers. And then you go through the underfill process, and that structure is then bonded by C4 assembly to the substrate. So that's the RDL first approach. So these options are all going through some level of R&D currently as well. Then there are hybrid options as well, where folks are looking at combining inorganic CVD processes for the fine line together with the organic, these are the CVD layers with the actual damascene vias, and then organic layers to create these interconnection schemes. And silicon interposer is actually the one in production today. So from Xilinx perspective, though not for HPM, but for die partitioning, we have used this. We are already in production with our second generation of products and ready to sample the third. So silicon interposer is a platform where you don't really have to worry about the interconnection density. Any old generation technologies such as a 90 nanometer or 65 nanometer could satisfy the interconnection for HPM. And so AMD actually came out with their Fiji product last year with the Gen 1, HPM Gen 1, which uses a silicon interposer platform to interconnect HPM to their GPU. So there is a whole range of options. So in summary, if you look at, if you classify them as a substrate approach or kind of a hybrid silicon bridge approach, silicon interposer or a wafer level approach, I touched upon all the the design rule aspects in my previous slide. What I want to focus here is, so silicon interposer is currently in production. And the hope is there will be lower cost options emerging also in the future. And our assessment is we think some of these approaches may come about in the 2018 timeframe or so. And Intel probably will be in production as well next year with the EMIB. So going to the design aspects here, so this is a layout of the bump features on a HPM. You have the phi region here, and the power delivery to the HPM. So each channel here supports 220 signals. So and there are 8 channels, which means you are looking at about 1760 wires to interconnect the SoC to the HPM. And when you account for adding in some ground wires and so forth to manage signaling at these 2 gigabit per second data rates, roughly about 2,000 wires is what you need to manage connecting the SoC to the HPM. So JEREC came out with some guidelines. So to run at these speeds and an UI of 0.8 or higher, you could conceivably have a 3-layer scheme with the 4 micron pitch, ground shield layer, and up to a max wire length of 6 millimeter, right? So the point to watch out is, but this particular scheme may not be readily usable in the sense, if you go with a 90 nanometer 4X technology from a foundry house, and if you wanted to stay with standard offering, you might not quite get a 2 micron thick metal wire, maybe more 1.2, 1.4. So the design templates have to be understood and tweaked accordingly. So the design methodology itself, if you look at it, there would be vertical routing and horizontal routing that needs to be managed. So in our case, for example, when we have high-speed IOs and GTs, and the GTs could push even 28 gigabit per second or higher, you have to be quite careful in how you design the vertical route. And so we look at models, both S-parameter and circuit models, all the way from microbump to the package pin. And also the TSVs in these cases are also more tuned to support these higher performances. So for example, parasitics become quite important at these high data rates. And silicon is, especially doped silicon is a lossy material, so we do pay attention to tuning the resistivity of the silicon substrate itself. And so on the horizontal routing, the design is no different than what you would do with a traditional single die design and extraction. So the microbump is extracted as a subcircuit, and you would combine all these different dies into a box die for LVS together with the interposer where you are extracting the metal, right? And then the entire combination goes through the simulation process. On the tool side, we don't use any tools that are different than standard from providers such as Synopsys, Mentor, or Cadence. But the PDKs themselves are customized. So for example, I think Kevin touched upon the HPM. The inside of the HPM, the memory side is a black box, but what we would get as a user would be all the netlist information and what needs to be supported, for example, from power delivery and so forth. And that goes into the layer here. And so TSMC has qualified the EDA vendors in their design reference flow. This is for the CoWoS platform, which is the silicon interposer-based platform. And that's something that should be available for customers who work with them. On the package tools, again, there's nothing too different than what you would use with the regular flip chip substrate design. So could be tools from Cadence, Sigrity, and other EDA providers. But the one aspect to be taken care of is, these designs are becoming much larger than what would be a usual monolithic flip chip design. So if you have SoC with 4 HBM, you're looking at interposers that are larger than reticle sizes. And maybe C4 bumps could be over 30,000, right? So from the versions of the tools, you need to be making sure that the data sets can be handled to simulate appropriately. So on the supply chain, we are qualified with TSMC's CoWoS platform. And in this particular approach, essentially an FPGA, GPU, or ASIC wafer, the wafers would go through a sorting process, usually before microbumping. And then the microbumped wafers are diced and assembled on the silicon interposer. So the silicon interposer wafer is still in a full thickness format at this stage. And the reason being is it lends itself to a very flat configuration from an assembly and yield perspective. That's very important, especially when you have when you have very large SoCs, a lot of micro bumps, right? And if you're integrating multiple dies, the yields need to be at above 99.99 something, right? So warpage management is actually a very critical factor. So in this configuration, then it goes through the assembly and molding and then carrier bonding. Then the interposer wafer is thin to expose the TSV and the C4 bumping, and you dice it and you package it. So if it were OSAT format, then clearly the interposer wafer has to come from a foundry, and you need to find a partner. So the supply chain is getting a bit more complicated because now you could have dies coming from a TSMC, memory from, say, Samsung or SK Hynix, and interposer wafer from another source. And the integration all happens at the assembly provider. And in the assembly provider case, there could be also 3 different integration flows. Could be a chip on chip on substrate first, or even chip on wafer. But here in this case, the interposer is fully processed before you would integrate the die. Because from the assembly provider's perspective, usually they are not so keen on having a lot of dollar value on a wafer when doing a bunch of post-processing on it, right? So all these options are available. And in AMD's case, for example, it's one of these flows that are used. So getting into some of the system aspects, I mentioned the thermal. So what I show here is a high-performance compute application with a PCIe card, right? It's a full length, full height, and the total card power could be pushing 320 watts. And with an airflow in this direction, 15 cubic feet per minute. And in data center applications, typically the ambient tends to run around 30 to 40 degrees C. So in this scenario, when you're looking at, see, one of the big things that has happened is usually the memory tends to be used on a board level, where the environment is a little bit cooler than on a package level. So you have moved it into an environment that is hotter. And so if you, especially on a silicon interposer, which can be conductive, the thermal coupling is quite strong between the SoC and the HBM. So you could be looking at the HBM temperatures getting up to 95 plus degrees C. And so going through the stack here, you could have a thermal gradient of up to 2.5 degrees or so just between the layers, and a total gradient of 12 to 14 degrees C. So now you can imagine when people are starting to push 8 high stacks, the gradient gets even worse. And as Kevin alluded to earlier, the memories are, the max junction temperature is usually rated to 95 degrees C. So it is certainly something that from a system level, companies have to pre-plan the cooling solutions. And also, the thermal models themselves are quite standard. Usually they are simulated in a flow therm or a ice pack environment. So now if you come to other applications, so telecom is an application where the thermal is even more challenging. And especially in these kind of environments, the upgrades may not be happening that frequently, right? So the customers could be looking to replacing legacy cards. So when you have legacy designs, that means the cooling could also be more limiting on what the options are available. So, and in these environments, the ambient also could be getting as hot as 50 to even 60 degrees C. And definitely, the temperatures could be quite challenging from a memory perspective. So, so I think there needs to be more thought that needs to go in this area, and hopefully, the sophistication of how you calculate the allowed maximum temperatures for the memory needs to be more detailed than just a blanket 95 degrees C, possibly. Right? So with that, I would like to conclude my summary. So there is definitely a strong motivation based on system power and low latency bandwidth to integrate HBM. Certainly, high-end gaming was the first application that came about, but these days, data center and other applications are also strongly pushing the adoption. So silicon interposer is the current, the incumbent technology today for integrating HBM, but certainly other approaches are starting to emerge that could potentially offer a lower cost path. And as we look at it from an end use or a system use perspective, there are certainly challenges. Thermal is one of them that I alluded. And if HBM has to become quite more broader, right? And here I mean more even industrial type of applications. These are areas that need to be looked at more closely. So with that, I would like to conclude my presentation, and thank you for your time today.
Great. Okay, we're getting down to the wire now. Everyone's getting hungry, I'm sure. Okay, our final speaker today, and then we'll have our little Q&A session, is Alan Rush. Alan Rush is a fellow at AMD. He focuses on imaging, computer vision, and machine learning. He has over 25 years' experience in research and development of imaging-related products. Alan has been the founder and key executive at several companies, including Sierra Imaging as CTO and founder, Foveon as vice president, and Nethra Imaging as CTO. So please welcome Alan Rush.
Thank you. Thank you. So where's my clicker here? Good morning. So I'm the last speaker between here and lunch, so I'll try to make this quick. They asked me to talk a little bit about applications as it relates to emerging memory technologies and some of the things that we see in very compute and memory intensive types of applications. So I thought what I would do is, instead of talking about things like applications that we already know about, so for example, data centers and networking, we already know about what the challenges are there. I thought I'd spend a little bit of time talking about some of the emerging applications which we know are going to be pretty popular in the years to come. And certainly the current examples and current applications are already telling us about some of the challenges that we have. So I want to talk a little bit about where we are in terms of the memory, compute, networking, interfaces, and things like that as it relates to high demand, high memory, high data types of applications. I'll talk about a little bit of in where we are with memory resources in these applications and what we're trying to do to ameliorate some of the issues that come about. And before I forget it, I also want to point out that from time to time I'll mention that it's not always about higher bandwidth, higher capacity, and lower power. Sometimes it's about application efficiencies and algorithm development. And in the case of machine learning, that's exactly what we're seeing. So what are the challenges and what are we doing about them in the current applications and emerging applications? And then finally, just a little bit of speculation about where we think things are going in the future. So everybody's aware now of virtual reality, augmented reality, and so forth. The fact is that this is something that started many, many years ago, albeit in a different form. And through the years, we've come to understand, basic 3D rendering and the use of shaders and advanced technologies to figure out how to render pixels correctly on a screen. We've reached a point now where the realism that you can generate in graphics is almost impossible to discern from reality. And now we're getting to the point where, physically you can see things in 3 dimensions by using a combination of virtual reality glasses and GPU and so forth. And so that's kind of where we are today, and things are evolving at a pretty rapid pace. If you look at where we were 2 or 3 years ago, the first Oculus was coming about, Vive was coming, and so forth, and there were lots of difficulties and so forth. And the point here is that a lot of people have spent a lot of time figuring out the challenges and the difficulties of those early products to the point now where we've got some pretty good products that are in use today. But going forward, we fully expect that as you're interacting with these systems, you won't be able to tell the difference between what you're actually seeing versus what's real. The goal, for example, of using telepresence in video conferencing, someday that will become real. And our challenge as technology providers is to figure out ways to do that in a way which is both affordable, low power, easily moved around, not too cumbersome with the user and so forth. One example, though, that's kind of in the early stages of becoming reality is the automotive intelligent car. And everybody's heard about the Google car, and there's lots of examples where experiments are being done now to figure out how to make cars more intelligent. Not so much from an autonomous driving perspective, although that is definitely one of the big goals, but also from the point of view of making cars more intelligent. One of the classic examples is doing gaze detection for lane departure warning and things like that. If you expand that and say, well, how many other things can we do in an automotive environment? The answer is lots. And in fact, what we're doing now is exploring and asking the question on the automotive platform, what are the things that are most important to both the comfort of the driver and the passenger as well as the safety of the car? And the answer is plenty. There's lots of stuff. And they all have some very common attributes and common things that we need to take into account. So for example, today, almost everybody has a car that has a backup camera, and that's, I think, going to become a law soon, at least in the United States and at least California. But what these guys are figuring out is that we need to see things from the car in every direction, both on the XY space as well as the Z space. And what's happening now is that there are so many sensors being put into the car that the data coming in is becoming one of the bottlenecks. So right now, the sort of rule of thumb is that they're going to have at least 10 cameras per car that are in the visible spectrum, at least 5 in the LiDAR spectrum, and 5 more in some other modality. And the amount of data that's being generated out of that is so high that there's a separate processor just to do the fusion, much less any of the machine intelligence. So to support all that and to try to make a case for how this is going to work, HBM and memory density in general is a tool that we're using to build products that can easily be integrated, that balance the needs of high performance compute power, high memory bandwidth, and high memory capacity. And so recently we've made some announcements. There are some new products on the market which actually take and put into production some of the techniques that we've heard a little bit earlier today. So the main idea here is that by adequately balancing the various elements within the system of memory, I/O, CPU, GPU, packaging, thermal management, and so forth, we can actually generate products that have the capacity and the ability to address some of these challenging applications. So, I mean, I'm not going to go back and review everything that we just heard, but this is an example of something we actually put into production. So the HBM techniques that you just heard about are actually being used now, and they're in reasonably good high volume production. So a lot of the hard work of getting it to work properly, getting the yields up, and getting the testing and so forth, a lot of that's behind us, and now we're in the process of getting these into the hands of customers where real applications can be developed. In addition, we're taking advantage of some of the packaging and shrinking the footprint of the overall card. So in the lower right-hand corner is an example of the Fiji Nano, which is one of the smallest PCI cards available and packs a lot of compute power and memory bandwidth to the point where you can actually get things now into a much smaller footprint from an overall packaging perspective. So we're not limited to things that are just visual in nature. A lot of the things that I do talk about, we focus on things that are highly visual, and what's the input, what's the output, what's the transform, and so forth. But there are other sensors, and there are other sensory types of issues that we need to worry about. And it turns out that in addition to vision, there's also audio, and audio is making somewhat of a resurgence. We're getting into the mode now of expecting three-dimensional, highly physics-oriented types of auditory responses and inputs. And so what's happening here is that we're not only seeing an explosion of vision type of data coming into to these systems, but also a number of other senses. And so the combination of all of these is requiring us to build scalable GPU, CPU accelerators, and high memory bandwidth to take into account the fact that there's a lot of data coming in, a lot of crunching that has to take place, and then in some cases, a lot of data going out, but in a lot of other cases, not so much. So one of the things that we focus on in terms of how to balance systems is called a roofline model. And this was developed, even though it was just formalized, some ideas several years ago by Patterson. It actually was in practice quite a few years before that, but Patterson was the first to formalize this. And what it says is basically, no matter what your peak performance is of your GPU, CPU system, or whatever, you're limited by the bandwidth of the available memory in the system. And in particular, you're limited by the bandwidth of the memory in the system as a function of the type of algorithm that you're executing. And so the upper right hand shows a graph from his paper which outlined a few of the various algorithms. And so depending on if it was a matrix multiply or a transformation or an image processing algorithm, different levels of bandwidth to peak performance were calculated and plotted on the graph. These are rather old. These are 4 or 5 years old, so the actual models are not important at this point, but the relationships are. In the lower left-hand corner, it shows a similar kind of a relationship, but this time plotting the relationship of the memory bandwidth as a function of different types of cores that you would use. So, for example, if you have a CPU core and it's very limited in its amount of compute power, you may have a very shallow intercept to the peak performance, whereas you've got a distributed GPU core, you can actually reach pretty high bandwidth to performance levels. The measure that we use is called arithmetic intensity, and basically what it means is how many operations are you conducting or using in your algorithm per byte of memory that you have. And obviously, the more operations per byte that you can get, the lower the bandwidth requirement. So that's why you've got this slope leading to a maximum performance. We use this a lot to figure out, how much do we try to trade off the clock rates of the CPU or the GPU versus the memory and so forth. And it's a handy tool to have when we're trying to develop some of these systems. One of the things that we are very interested in, we're studying pretty hard, is that we know, for example, in graphics and in VR, we pretty much understand what those relationships are. They've been around for a long time. The algorithms for shaders and rendering and so forth are well known. What is evolving is some of the applications in AI or machine learning where the amount of innovation is rapidly changing to the point where some of these graphs change almost month by month, where we figure out that there's a different way to do some of the convolutions, so there's a different way to do deep belief networks. And in those cases, what we're finding is that as the machine learning community gets more mature, they're paying attention to two different things. They're paying attention to the accuracy and the overall system load, and they're also paying attention to the efficiency of the algorithms. So this is an example of how one would look at this, starting from sort of the ground root elements of the arithmetic. And the point here is, and we don't need to go through the details, but the point here is this stuff has been around for 20 or 30 years, and only recently, since 2012, have we actually seen an emergence of a combination of efficiency in managing the memory, as well as the improvements in the algorithms to get to the point where machine learning is actually useful. Today, we've reached the point now where a lot of these classification algorithms are within striking distance of human parity. So the next steps in going forward, and we're working pretty closely with the machine learning community, is to figure out how to not only continue making progress on the accuracy of these algorithms, but also to now figure out how to make them depend less on memory and less on memory bandwidth. Because, frankly, some of these algorithms work well, but they're heavily brute force algorithms. So, as I mentioned, the machine learning community's been working at this for the last 30 or 40 years. The artificial neural network was actually invented, I think, in the 50s or something like that. And quite a bit of progress has been made, but the major progress that was started to get to the point where we actually have a useful platform. It was in 2012 by Alex Krzyzewski. And so since then, there's been an explosion of innovation. There are new papers every year which push the envelope. And we've reached the point now in present day where we have complex deep neural networks and deep systems that can do very, very good at classification, recall, and so forth. There are lots of variations on a theme. There's RCNN, there's LSTM, and so forth. They're all getting very, very good response. And in general, all of them are making improvements. And the phrase I like to use here is that we're in the region now, or in the time now of we are training to learn. So the systems are being trained to learn how to do stuff. As we go forward and as these algorithms get more mature, the memory and processing balance is continuing to improve. It's my thinking that we'll reach a point probably in the next 3 to 5 years where we have systems that actually learn how to train themselves. So, you know, we saw an example of automotive. That's kind of the poster child for machine learning right now. Everybody believes that somehow machine learning is going to, you know, be a major enabler for the smart car of the future. But it turns out, of course, there's lots of people interested in machine learning, and in different forms and in different methodologies and in different environments, all of these applications are waiting for, effectively, good machine learning solutions. And invariably, that translates into extremely large data sets and the ability to get to large databases and information, either in the form of imaging or in the form of database entries, to help the process of getting through the learning and then obviously into the inference part. So where are we going in the future? I think that today we have a situation where the newer memory technologies are enabling us to put together systems that can do quite a bit. We're on track to have the advanced VR systems of the future where photorealism is what we would expect. We're on track to have machine learning where we can get training not so much in days or weeks, but in minutes or hours, and inference that's essentially real time. Going forward, however, it just seems like we have to do more of the same. We don't see an end to the bandwidth problem. We don't see an end to the capacity problem. Notwithstanding the efforts of the researchers to make improvements on algorithms to reduce the requirement for all of this, most of the new algorithms to make these things work properly are largely brute force. One of the earlier talks mentioned the idea of logic and memory. We're a strong believer that any way we can, you know, make the trade-off between how the processing element works and how the memory is instantiated is a good thing. In our GPUs, we have very sophisticated ways in which we have local memory next to the PE and ways to exchange it through the caches and so forth. And we sort of look at this as all of the above. We will take all of these opportunities to improve the overall efficiency of the combination of the processing element and the memory. We think that you know, going further in 3D is certainly a good thing. We've heard quite a bit of talk about some of the problems and challenges with respect to thermal management, and indeed that's a major focus for us as well. We think that getting teraflop level GPU is good, and we have lots of customers who want it, but we also want teraflops of compute power with a combination of memory at lower power as well. I didn't mention too much about big data, that we've already heard a little bit, but the fact is that we are now seeing an explosion, an exponential increase in data that's going to the cloud. We think that the training requirements for machine learning are the motivators behind how to get that data in a usable form. We have talked with all of the major network companies involved here, and all of them believe that at the end of the day, they're going to have enormous amounts of data that have to be sorted, sifted, classified, and resolved within seconds of being uploaded. Some of the numbers I've seen suggest that on every minute there's an equivalent of about 5 hours of video uploaded. And you have to ask the question, who's going to see all that video, and how are they going to see it, and how are they going to pick it? Those are all deep learning types of questions that all of them are looking to solve. It takes a fair amount of compute power to figure out the training. If you look at the ResNet or ImageNet or any of these databases that require a standard set of training, some of these can take a day, a week or so to do. They're looking to do 1 billion parameter training within minutes of receiving the data. So these are the sorts of challenges that we see. And in fact, the secret to the success here is going to be how to effectively manage all of that data, both locally as well as often in offline storage. So, I think that this is this is not an ending thing. We see this going on for the foreseeable future with no end in sight. And one of the challenges that we continue to face is how do we make that balance between memory, processing power, and throughput. So just to summarize, so there's a lot of factors driving some of the newer applications. Some of these are applications that we've known for quite some time. We're very familiar with. We know how to put them in the proper metrics. Some of them are rather new, and we're experiencing a learning curve even as we try to build products to serve them. The overall balance and capacity challenge for us is continuing. As I mentioned, we use a roofline model and some other metrics and tools to figure out how to best put the balance of bandwidth and compute power on the application. Machine learning is certainly one of the newer applications that have a high demand on both memory as well as memory bandwidth. And in the context of putting together nodes, even single nodes of GPU or multiple nodes of GPU with machine learning, this is a huge challenge for us. We are always looking at newer applications that require us to think differently about the memory compute boundary, and the idea of putting in logic and memory and so forth is something we're very much interested in. And then finally, I talked a little bit about some of the challenges on the big data. So that's it. Thank you.
So I'll just ask you to stay here. We'll get some chairs
Sure.
out. Okay, we're gonna have to actually have some time for questions. This is great. Just give us a minute here. We're gonna reconfigure, get our speakers back up on stage, set up some chairs. I guess while we're doing that, this is actually the first time, because I mentioned earlier that Vidya actually put this presentation together, and I think she did a fabulous job. I was just the first time I had seen all the presentation together. And a couple of notes that I took while I was listening was that we actually spanned a wide gamut. In previous Hot Chips, we've talked about memory technologies. We've had tutorials on memory technologies before, and often they've been very device or physics focused. We actually started, talking a wide range of the devices available. We went down to some new devices. We talked about 3D stacking. We talked about packaging technology. We talked about processing in memory. And then we get some great examples of different ways to incorporate HBM. And then we ended with applications that are going to require some of these new technologies. So I think there's lots of things we can talk about here. And unfortunately, my notes are really jumbled. So hopefully you guys will have really good questions too. But I've got a few that I wanted to start with after we get
the other guys.
everybody on stage here. So just give us a minute to reconfigure. You guys ready? Oh, perfect. Do you have any? No, just sit down. Or stand, or I'll have to stand over here because I have a mic. So, so let me just ask you guys a few quick questions, and then we'll go to the questions in the audience. So let me just start out the discussion a little bit, really high level. Let me get my notes together here. So actually, the first one I think is probably for you, Thomas. You had mentioned we've introduced hybrid memory cube, HMC. I always get those acronyms confused. HMC back in 2011, right? Sorry, you can't hear me?
We can't hear you very well up here.
Oh, really?
Yeah, there's no stage monitor. There's no stage monitor.
Let me speak up. So we introduced, or Micron introduced 3D memory back in 2011, and you had mentioned, some of the cost challenges that you've been facing. I'm just curious, what applications have you seen kind of adoption of the technology where they really need that level of integration or that level of bandwidth?
Yeah, so in general, the applications are, it's not all in one category because some people are concerned about energy. Some people are concerned about bandwidth or reliability. So the two main areas where we actually have go into production.
Can you guys hear him?
It's cutting out. Testing the new battery, thank you. Okay. So we've seen a few different areas of interest. Because the price per bit is higher, it has to occur in places where people value some of the attributes. And so in HPC, we've seen some adoption. You see a customized version of the HMC on the Knights series of processors from Intel. You actually see adoption in the networking community. And so these are places where reliability is really important. The bandwidth, of course, was quite important, as was the energy per bit. But the higher volume things like, let's say, a data center, it just hasn't hit a cost point yet that they can accommodate.
Okay, great. Yeah, I think was there still an echo on that? Did you guys hear okay? Okay, on the stage it sounds a little, but that's fine. Okay, one more question and then I'll go to the audience here. So, let's see, I had so many notes. Okay, some of the other high-level things I got from the talk, we talked about, differences in HMC and HBM. They both seem like ways of increasing bandwidth to memory and using 3D stacking technology. It's all interesting. But what I was kind of curious about is, I think, Suresh, you were talking about different interposer technologies and potentially using older technologies like 90 nanometer, but that the JEDEC standard requires a different metal pitch. And so I wondered, once you factor that in, does that make using the older technology potentially more expensive or harder to use until it becomes, mainstream?
I think from our view, we don't need to do any customization of the interposer PDK. It just means there needs to be more effort in coming up with design templates that can still push to the 2 gigabit per second. Not everyone, I think, can offer, for example, 2 micron thick copper metallization.
Okay, so we're going to take questions from the audience. I think there's mics on both sides, I think. It's hard to see from here. Please, when you get up to the mic, just mention your name and your affiliation, and we'll take your questions. So we'll start over here.
Hi, my name is Nakamura of Cool Chips. That is a hot chip. Prior to applications issues, I would ask you, thinking of pre-charge and pre-charge, probably DRAM is very slow. Speed is very slow. So what do you think of speed up of DRAM itself? This is my questions.
Okay, I think it's a little hard to hear the question, but I think the question is basically about the speed of DRAM, and I assume by speed you mean latency, that the latency hasn't decreased at the same rate that the bandwidth has increased. Is that about?
Probably correspond to high bandwidth would be correspond to speed, but DRAM itself should have speed up
Okay.
much more. No,
Right. And again, what was your affiliation? What company do you work for?
me?
Yes.
Oh yes, I'm a university people. Sorry.
Okay. Gotcha. Okay. Who wants to? So one of you guys want to talk about?
I guess I'm the youngest here, so I'll take it first.
Okay. Go ahead, Kevin.
But we've seen the disparity between performance when we compare DRAM versus a CMOS logic, and it's inherent in the design itself. In order to improve the DRAM speed, we're talking about many key parameters. DRAM speed or latency can be improved, and we've seen this. Micron has commercialized this product with the RLDRAM, for example, where you have to reduce the mat size or the block size of the DRAM. And that basically allows the device to cater to a specific market. But in terms of DRAM itself is a very tough business to be in. We live on the scale of volume. And so DRAM technology is mostly, as you've seen, driven by the computing architecture where speed or latency is not as critical as the bandwidth. And so from a technology perspective, you have to take into account the technology process capability and also the economic viability.
Amen, brother. Additionally, though, of course, as you say, Micron actually has commercialized a product we call the reduced latency DRAM. And I was speaking to someone earlier about that. I love the product name because it's so misleading. It isn't about the reduced latency as in not reduced data latency. It's in the ability to have a higher request rate per available responder. And so it's a higher bank count device and a much lower TRC. TRC is the time it takes to go back to the same resource that you had just been to before. And so we do have one version of the chip that is 6.7 nanoseconds of TRC versus the standard DRAMs that are, call it roughly 40 nanoseconds. So so our capability is to have better response time, but as was correctly pointed out, there are economic consequences of speeding that up. Higher bandwidth also costs you extra die area, right? So every little thing you want to do has a cost, and then it's about that global trade-off between how many banks do I have, how many channels, what's my concurrency, what's my latency, what's my TRC, and what's the right economic solution for a particular market. And if you go after a low-volume market, you're never going to get the cost either. And so volume is another tangible factor that impacts that too. So we're trying, but we still have to keep in the realm of high volume, or we won't get the economy of scale.
Hi. Michael Shea from UC Berkeley. I wondered all these logic in memory and processing in memory, all these things, and the 3D stacking of all structures. Could you comment on the limitation of the air cooling and liquid cooling? Air cooling and liquid cooling for the structures. Eventually, we'll have to put together for the learning in the memory or logic in the memory or processing in the memory.
Yeah, if I can just add on to the question is, so it's about using different cooling technologies for some of these new functions, especially like if you're going to do processing in memory.
Yes.
And one thing that I would add to that is I think one of the speakers, I think Suresh, you had some amazing pictures, right, that show the temperature differential between the bottom of the stack and the top of the stack. And I would imagine that has some impact on performance, or at least the specification for what the worst case or the variability in performance is. So can anybody comment on what kind of cooling technologies you're looking at that might ameliorate some of those problems?
Yeah, I'll take a shot at it, but I think Suresh probably has some additional information. So yeah, cooling is a big challenge. So there's no question about it. And from a design perspective, I mean, the first order is to not generate heat in the first place. So that's one of the big focus areas, at least from the logic and core development perspective. One of the things that we see is that there's a high dependence on residual capacitance and clock rates that are the byproducts in generating the heat. And so when we put together sort of the advanced core, very complex collection of logic, that's all optimized for the die itself. Now when you move to LIM, you have to take into account the fact that the techniques that we might use for pure logic on a chip perhaps have to change when we consider the integration of memory or logic and memory types of configurations. So that's the first order. The second order is, we've seen now several generations of liquid cooling and pretty much any high performance compute type of situation where the density is so high that you have no choice but to do it with liquid cooling. Certainly in lower performance and lower cost type systems, we would expect air cooling to continue. But the motivation to use LIM in the first place is more on the high performance compute side than it is on the APU or the embedded types of devices. Suresh?
And additionally, I think about processing in memory is the last target is we have not the cooling system, because in the innovative application, like as the VR or MR is the if you think imagine there is the cooling system or a lot of the battery, it is not this server. I think the processing in memory is very essential for the mobile device. So the last target is no cooling system.
And since the mic is in my hand, I'll say one little thing. I don't want to be a mic hog, but a lot of people, when they say processing in memory, that isn't really what they mean. They mean processing at memory, rather than things actually being processed inside a DRAM node. I could talk about that, but I won't.
So I think there are probably a couple of aspects to this. Liquid cooling is still considered a more expensive solution than air cooling, right? So if these are newer applications that are looking at using these components, and people can design in the cooling system, there is definitely an opportunity that they could implement a more advanced solution, right? So, but still the thought process is, because of the, especially the OpEx expenditure is what, say, a data center or even a telecom customer would look at. Air cooling is always the first one they would look at to see, can I still cool it that way, right? So even with air cooling, I think it depends on what they could really push their solution to. Maybe it can still be viable. But the challenges from our perspective, okay, sometimes it's not so visible from the end user standpoint, what exactly can you get for your component as a cooling, right? So what we would like to see is maybe from two ends. One, as a designer, we always get one number, right? Meet 95 degrees C for 24/7 operation. In reality, if you look at it, it's never that way, right? I mean, even in a data center, depending on the time of the day and the workload, there is actually a profile. But that kind of more intelligent modeling, I think, still needs to evolve, which can help. The other aspect is we'd also like to see from memory how to get a better, more, I would say, almost workload-based map, right, that we can accurately model from a reliability standpoint. So those are things that we would like to see from as a user perspective.
We have a question over here on the right.
Okay, thank you. Nathan Brookwood from Insight 64. I'm an analyst who follows the chip industry. I have questions for both Kevin and Suresh, and since Suresh has been doing most of the talking, I'll start with Kevin. You talked about how HBM solutions can save 70% on power compared with a DDR3 and DDR4 solutions. Can you give us some broad overview as to how that power saving is accomplished?
Sure. When we compare the power, it's an effective power. So basically the power that you normalize over the bandwidth that you get. And so when you, in order, for example, with an HBM2 solution that from SK Hynix that delivers 256 gigabyte per second, you would have to have a bunch of discrete DRAM devices or DDR3 or DDR4 together. If you can just imagine the number of external IOs that the processor would have to drive to, and also the distance between the processor's PHY to the memories on the PCB layer, every inch of millimeter or centimeter away from the processor will increase the power that the controller would have to drive on the I/O. So by having, first of all, a very high bandwidth, wide parallel I/O interface, and also on top of that, the HBM device sits right next to the processor, you're able to reduce the I/O driver size, and also that's how you realize the power savings.
So it's a reduction of the number of devices and shortening the distance between the memories and the controller.
Correct.
Are those the two big things?
Yeah.
Okay, cool. And then Suresh, you talked a lot about chips operating at 95 degrees C and such. You never said anything about issues of CTEs and matching CTEs for substrates and silicon. Are any of those kind of factors an issue in the different kinds of approaches you addressed?
Yes, so that is actually a very, very important area, and a lot of development and R&D has really gone into addressing those sort of mechanical aspects. So I would say now, in our experience, at least from the silicon interposer platform, the solutions are more mature now. But still, I think Kevin, in his point, alluded, right? We still have to design two different interposers based on which HBM vendor the memory comes from. And even size differences in the memory of a millimeter can drive that kind of decision-making because of the issues you precisely mentioned. And but that's still the reality today. And I think as some of these newer options that come about, like I alluded to the organic options, they will have to go through some similar learnings there as well.
Okay, thank you.
We have a question over here.
Hi, my name is Matthias. I'm working for YY as a system architect. My background is HPC. I worked at Cray and HGI before. And my question is, back in the past, most algorithms were very compact and dense matrices, for example. in the new algorithms, deep learning, for example, much of the data is very sparse. So I wonder if memory architecture has to take these new access patterns into account at some point, because the data will be much more sparse than we had in the past.
Yeah. My mic's still on. No, my mic's still on.
Oh, okay. Well, I'll answer anything. So, yeah, we've certainly seen that that phenomena in a lot of different problems. You cite one of them, but you get a few phenomena happening, and that is one is the very heavy randomization of the addresses that the memory will see. And so in the past, you could actually take pretty good advantage of a page being hit more than once. And so you look at the mainstream stuff, right? It's based on a DIMM. You've got 8 DRAMs that light up on the DIMM. Each one has a particular page size, so the overall is 8 times that. And you would get pretty good revisitation of those open pages, so a lot of people had open page policy. Well, once the workloads get really complicated, partly because of sparsity, partly because data can come from or to anywhere, and we see a tremendous randomization. And so that's making the traditional models that are used, frankly, in DDR3, DDR4, and HBM, those style of access models actually work very poorly now. And so it does demand that we do something about it. And so HMC actually does that, doesn't go far enough. And so there's a plain need for us to evolve further than what we have. And so that's a future device I hope to be able to talk about later, but today is too early for that. But thank you, that's, it's a very good observation.
Perfect. Okay, let's see, we were there, okay, over here.
Jose Renau, UC Santa Cruz. When talking about HMC at HBM, we are saying price points expensive, but there is no prices or relative prices. So what I'm trying to do is, let's assume that DDR is 1. Can you say, what's the price do you think is going to be the competition? You don't want to say yourself. For example, Hynix can say, oh, HMC in 2 years, I think it will be priced this X over DDR, and maybe the opposite. Or you can say yourself if you want.
Yeah, you want an HMC answer, an HBM answer, or both?
Both.
Both, yeah.
Actually, if I can add one thing onto that too. When you talk about HBM, how do you calculate the cost? Because there's a lot of different.
I'm talking
right?
per part.
Yeah.
You have the silicon, not the silicon interposer part.
Yeah.
Yeah. So, you know, we're in a public forum, and any smart person would never touch that question, right? Because they'll get barbecued once they go back to their company. But
that's why I said the competition.
But I'm not afraid of barbecues. So, you know, generally, so let's look at HMC. Okay, you have 8 DRAM layers, right? Each DRAM layer costs more than a normal DRAM because we have the overhead of TSVs, both processing cost and the area. And then we have a logic die under it, right? So you know it's not 1.0x cost per bit, yes, right? Pretty obvious. What is it? That will depend at which year you look at and what's the
2 years from now.
What's the possibility at the mature price level. And so from that pure perspective, the HBM has a little bit lower cost potential than the HMC if you only look at that initial, the silicon that you're buying, but then you have all the massive integration issues, right? So we've seen both sides of it, right? Because Micron does HMC, we have the HBM designs as well, and we've seen through the eyes of our customers the difficulty that they have. The HMC is a much easier integration because it is a ready-to-go product for the most part, right? HBM has a lower initial acquisition cost, but then you have to pay for all the engineering for the thermal analysis. And you saw the slides that had, here's 12 steps that you have to go through in order to get it designed in. And so if you have a very high volume design, you'll amortize those costs and probably come out better. If you don't have that high a volume, then you're going to end up with a lower life cycle cost by far on the HMC. And so, we really leave it up to the customers to look at what's best for themselves. But in both cases, in this vicinity of time, we're looking at something more than 2x cost per bit when you really figure out everything. We actually had some we lost some HMC designs to HBM because there was a perception it was cheaper. And 9 months later, they came back to HMC because they figured out that they weren't better off. So it's a
But in the
fluid
2x,
situation.
not like 5, something between 2 to 3x is a reasonable range.
I think that's probably a reasonable assumption, but don't go writing articles about what I said because I'll get killed. And I hope you like me enough to not want to see me dead.
So the rule of thumb is do not trust an engineer when he gives you pricing.
Sure. Trust the marketing guy instead.
And the second point is don't trust the marketing guy. But actually, your question is a fundamental question that a lot of customers ask. And I would give you an analogy of I want to travel to China, and I asked the airline industry, how much does a seat cost to get me to China? Now, the question is, how are you going to get to China? Is it on a commercial airliner? Do you want to get on a fighter jet? Do you want to take a rocket to China, for example? So when you compare an HBM or HMC solution to an existing DDR3 or DDR4 discrete devices, it's actually not an apple-to-apple comparison because the characteristics, the performance of the device themselves are much different. What we do from an application level is compare the benefits that you get by implementing an HBM or HMC device versus a DDR3 or DDR4 external DRAM devices. So when you look at an ASIC or a processor to implement, X terabytes of bandwidth, for example, a terabyte of bandwidth per second, your I/O on the beachfront of your ASIC would cause your ASIC die itself to grow tremendously that it's impractical, and it costs so much that you can't design the ASIC. And we see this with Xilinx when they actually break down. This is from an FPGA perspective. When they break down the die into smaller die area, integrate that onto a silicon interposer, they're able to realize much better cost saving by having better yield on the die. Performance is the same for those small die versus a larger die area. And so when we compare costs for an HBM, to answer your question, it's not apple-to-apple comparison, one unit to the next unit, or not even 1 gigabit of HBM or HMC versus a gigabit of DDR3 device. You have to take into consideration a holistic view and the benefits from that.
Yes, my name is Eric Chu. I work at Google working on the consumer hardware. And my question is, Intel just announced that it's going to open its foundry process for ASIC designer. So as a SoC architect, I always want to customize the DRAM for performance and power. So is it a business model for you to provide differentiating technology for SoC architects?
I think we're missing a little bit of the question because of the mic cutting in and out. But basically you're saying, do we intend to have differentiated products depending on the SoC architecture?
Exactly.
And I think, of course, the three of us are all in the same boat, right? We need high volume, or right away the cost isn't going to be that good because that's the #1 driver of the cost. And so the one nice thing about HBM, if you don't mind me complimenting that work, I want to see HBM successful, by the way, because it develops infrastructure that benefits everybody. But with HBM, you can do some of your own customization even though the DRAMs are not different, right? And likewise with HMC, we do have custom logic layers that let it be different, which is what Intel did, right? The bottom layer for the Knight series is totally different than what we have for the general market. And so we have to walk that line between still maintaining good volume, but allowing enough diversity that you can accomplish things that you need to do that might be different than other players.
Yeah, exactly. The HBM is a possible solution, but that's cost prohibitive.
Okay, I think we're just running into lunchtime here. So a couple of notes. We're going to, I'm sorry? Oh, okay. We'll take one more question at lunchtime.
Okay. Devendra Tripathi from Broadcom. I have a quick question that in a typical number of latency from logic to logic, would somebody answer, either Xilinx or, this for HBM by the way. Logic to logic, what is the typical latency?
It's logic to logic.
Yeah, from the ASIC to ASIC, what is the latency? No, the round trip.
ASIC to ASIC, yeah. Suresh.
So I'm not a design guy. I'm not sure I'm the best
So the question
person
is,
from Xilinx to answer, but
interconnects. What's the latency?
So I think from our experience, let's say we could we have designs that run more than 500 megahertz, for example, right? Connection. So you could probably.
Are you saying that 2 microseconds?
Well, so like I said before, I'll answer any question. So if you're just talking about pin to pin, that's one thing. But if you look at a typical SoC, let's say a 32-core CPU chip, things have to go, so it depends where to where, right? You have to go through a network on chip. And so if you happen to be unlucky and you can't communicate through your local zone, then you can easily be looking at another 30 nanoseconds on board before you can even get off chip somewhere else, right? And so I think it's impossible to answer the latency question because you have to have all those details filled in. But that's a good example, right? 30-ish nanoseconds for a network on chip plus whatever the external interface is. You can talk to Bryan Holden later about some good chip-to-chip interfaces. He'll sell you one.
No, sorry, let me clarify. This is about HBM, and you have interposer, you have the logic, and you have memory. My question is from logic to memory and going back, what is the latency in that setup? Typical latency. I know this is the question.
So I think the question is basically what's the latency for an HBM read access, for example.
There you go.
Right?
Yes, that's right.
So,
what is typical read latency?
I mean, pick a number.
Yeah. We can talk more. I think we have NDA, but this is a public forum, so can't really provide all the preliminary numbers. But HBM, it's a DRAM technology, so the latency is still DDR3, DDR4 range. So you can use that as a reference.
Okay. All right. We are bumping right into lunch. It should be ready in the back. You have tickets in your holder. We're meeting back here at 1:45 for the next tutorial. I'd like to thank our speakers. I think they did a fabulous job, and a round of applause. Thank you.